Okay, good afternoon everyone. Assalamualaikum warahmatullahi wabarakatuh. Today we will have a guest lecture from Professor Victor Krisanov from a society laboratory, Ritsumeikan University, Japan. Maybe Professor Krisanov, please.
So thank you, Budi, for your brief introduction. So ladies and gentlemen, good afternoon. Are you ready for a long and difficult lecture? No? Not really, right? So before I begin, I have one request to you. If you fall asleep, okay, please don't snore, okay? Okay. So, but seriously speaking, my request to you is that, well, first of all, the material what I will talk today about is quite difficult. So it's easy to understand at the conceptual level, but relatively difficult to understand the details. Whenever you feel you are lost, but still you would like to follow me, so don't hesitate to interrupt me, like raise your hand, wave your hand and ask the question, okay? Interrupting me during the lecture is fine, absolutely fine. So of course, in the end, I hope we will have some time left for questions and answers, but also during the lecture itself, don't hesitate. So then our topic today is sustainable machine learning, or more generally, more broadly speaking, so sustainable AI. And this is what I'm going to talk today about. So first, I'll provide you with some interesting facts about machine learning, about artificial intelligence. You guys all, of course, know what is machine learning, right? So, and of course, I believe that pretty much all of you were involved into training a model, using an AI model, yes, in your classes, in your projects. So, and even if you would say, no, I don't remember, so still you are using AI models on a daily basis. So every time you use your smartphone, well, you deal with plenty of AI models. So then why should we talk about sustainability? Yeah, and what would it mean? Yes, so sustainable AI, it's just words, but we are not politicians, we are engineers, right? Yes, so whenever we say something, so we need to provide the relevant technologies and details, yes, so not just slogans. So then in the beginning, I will again provide you with motivations and explanations why it is important, yes, so to talk about sustainability in the context of artificial intelligence. So next, I will introduce you a very new, I would say brand new method, so attributed to the so-called green AI. By the way, what is green AI? Also, I will talk to you about it in a few minutes. So a brand new method which would let us be more responsible, more sustainable, you as well, whenever we do something with something means that, well, in the technological sense, we develop, test, yes, or deploy machine learning models. So more specifically, I will introduce you to the so-called LMD-FIT benchmarking method, so which was recently developed in our laboratory, in my laboratory, yes, so where I am from. So, which was publicized and which is already used by many researchers. So that's pretty much for this lecture. So in the end, of course, there will be conclusions and references to some additional resources, so which you would use both to better understand the method and also to use it in practice. So then let's talk for a little bit about motivations. So again, we are here all IT specialists. In these days, to be an IT specialist means to deal with machine learning. Yeah, it's pretty much unavoidable. So to deal with machine learning means to train, retrain, fine-tune, yes, or test, select, deploy, yes, or many different machine learning models. This is a fact that in the time span from 2012 to 2019, that means that just over the 7 years, the amount of resources, computational resources, and pollutions, carbon footprint pollutions connected to the resources used, increased 300,000 times. Can you imagine it? Like over 7 years, there is a technology which made people spending 300,000 times more in terms of the resources and, well, in terms of the negative effect, negative impact on the environment. So is there any other technology than AI? No. So the amount of pollutions, what you guys and me as well, of course. So what we produce one time training a machine learning model on a GPU, an average model, not like LLM, large language model, no. Those models, for instance, like image classifier or text classifier or whatever classifier, yes, so machine learning model, we just use an average GPU, such as, for instance, RT 30-something or even 20-something. So the amount of pollutions what we produce by consuming the energy, so is equivalent to what is produced by a car in 6 months. Okay, that's amazing. Yeah, think about it again. It's no kidding. All what I'm talking here about, these are facts. It's not just my imagination. So these are facts, and these facts were reported in reviewed professional periodicals in journals. So also, when we train one model, so the pollutions, carbon monoxide, carbon dioxide, yes, so emissions, so produced by electric power plant generators, so is equivalent to those what one human being so produces over the year. So that means that we are breathing, right? We are polluting, of course. So, but, well, we are in no competition with GPU in this sense. So recognizing this tremendous trend, actually very harmful trend, no good trend in the technology, so researchers started to think, well, perhaps we should do something. We should shift the focus in artificial intelligence research from efficiency, from accuracy, from all those F1 scores, so to what? To optimization. So instead of focusing on just the accuracy, so how performance, let's say. So, well, we also need at the same time think about how harmful in terms of the pollutions, in terms of the emissions, what we don't see immediately, but what anyway are produced and associated with AI, yes, so to these pollutions, this impact on the nature. So we need to minimize them together with maximizing the performance of the AI models and AI methods. So to officially kind of like introduce this demand for new approaches in artificial intelligence research, so it was suggested to introduce the new term, so green AI, where again the focus would be on minimizing the environmental impact while maintaining still acceptable accuracy, still acceptable performance of the models. So green AI is a relatively new term. Yes, so however, well, the number of people involved in green AI research, yes, so increases, yes, so well, rapidly. So the governments worldwide, yes, so support, yes, so this initiative. So, and you guys, yeah, you need also to start paying attention, so to green AI issues, because very soon you will be engineers, you will be IT researchers as well. So now the usual traditional AI is called red AI. Red means that, well, again, research which only deals with performance, not taking into account the environmental impact as well. So then, good, green AI. This term was introduced and publicized widely, so about 5 years ago, 5 to 6 years ago. So there were quite a few publications. If you use, for instance, Google Scholar, so, and just type green AI, yeah, you would find quite a few papers. Unfortunately, there is a problem with green AI research, yes, at the moment. Most of the publications, most of the projects which have already been finished or right now being conducted, so they're aimed at the estimation of the environmental impact, so of one or another technology. So very few studies were trying to introduce specific methods which would help us move a little bit closer to the goals of green AI, goals of minimizing the harm to the nature, goals of minimizing of the carbon footprint, so due to the use of artificial intelligence models. Why is that? Why many studies which estimate, calculate, yes, so, well, the environmental impact, and why very few studies which really try to propose specific methodologies which would help us minimize the impact? Why? Perhaps one possible answer, and the right answer here, would be, well, because we know that there is no free cheese, right? You know this saying, no free cheese. If somebody offering you a cheese, it must be what? A trap, right? So here as well, we want accuracy, we want performance. So we means the researchers, we already been optimizing. After all, we are not idiots, right? Yes, so we always try to optimize, yes, so computational resources required, because, well, if our application, if our AI model, our AI method demanding too much resources, nobody simply would use it. It would be too expensive to use. So money here, therefore, they come also as a hidden kind of like optimization criterion as well. So, well, since we already are trying to optimize the cost in terms of the money, yes, so of the AI models and methods, what we develop. Indirectly, very often, so we also kind of trying to, at the same time, to reduce the environmental impact, because the more computational resources required, the more environmental impact and the more expensive, yes, so the method what we would offer. So that means that we already been doing it. Not just saying about it, maybe not realizing it. That's why, yes, so, well, perhaps there are no breakthroughs right now. So, and right now there are no revolutionary methods. So does it mean that, okay, we just a little bit talked about green AI and we should stop and forget about it, and it's just saying that, yeah, anyway, we've been doing it. We are always striving to devise methods, yes, so which would be not so much, yes, so demanding in terms of the resources. It wouldn't be a good idea just to forget about green AI, however. So green AI, it's not just about optimization, but it's a call to the research community, to you guys, to the new generation of researchers. So to be creative and to come up with new methods, so which would again, yes, so I repeat it again, would aim rather to re-examine the existing technologies, the existing methods, and try to minimize the environmental impact of the broad introduction of artificial intelligence models. And that's exactly how we looked at that in our laboratory. So, and well, our study into the green AI began at a very conceptual level. Okay, what does it mean sustainability in a very broad sense? It's not a new concept. For instance, sustainable manufacturing, this is a term what was very popular some 30 years ago in the research community. Manufacturing, not IT. Yeah, so the traditional engineering, as we say. So sustainable production, sustainable consumption. Yeah, so, well, again, this what has already been done in many fields. Usually sustainability, this is about 3R. Yeah? This 3R framework is pretty well known, used and introduced, so in many countries, by many governments, in many fields. So what is this 3R? Reduce, reuse, recycle. So we started to think, okay, our goal in green AI is to minimize the environmental impact. So what would it mean for us to reduce? Reduce means, well, reduce the computational resources demand. So try to develop systems which would work on, let's say, even the minimum computational resources, which would not require, 25 GPU, installed GPU servers, and so on and so forth, and would still work and work satisfactorily with do what they intended to do. So that means that, well, reduce, it's about computational resources required. Recycle, this is about reusing the models, recycling the models. So AI models which have already been developed. We are doing it, you are doing it, right? You guys, what? You are using GitHub, right? Yeah, sometimes you submit, an AI model, to your teacher from GitHub, right? No? No? You develop every time, your own models? If you are doing it, it's not a good idea, guys, yeah. So, yeah, recycle. Nothing wrong here. So resources such as GitHub, and not only GitHub, Hugging Face, for instance, and so on. So platforms provide us with great opportunities so to share with the research community, with, well, the current community and future researchers what we already done, what we achieved in terms of models, in terms of algorithms, in terms of data. So that people wouldn't need to reinvent, and repeatedly redevelop, things what already once been done. So recycling, therefore, well, again, this is just about our willingness, about our focus, on reusing the models, what already been developed. So then reuse. Reuse and recycle here are kind of like tightly connected, because reuse means that, well, recycling means getting a model, already pre-trained, for example, artificial intelligence model, So, but then to reuse it, very often we need to, as we say, fine-tune, we need to adapt, the recycled models to our needs. So that's about reuse itself. So the 3R framework, therefore, it's nothing new, just conceptual. It's not yet about any specific method or algorithm. It's more about the research practice. And we're already doing it, and you're already doing it. Fine. So if you follow this 3R, you're already moving closer, to moving all of us, so not just you, moving closer to green AI. What else? What else? This is just at the level of the methodology. Next, this is just our observation, and perhaps your observation, you would agree with me as well. Whoever developed an AI model, you know that usually we can't right away end up with just one model. As a rule, we have some alternatives. For one very same task, for instance, image classification. So, for instance, like similarity assessment of, let's say, some documents. So, as a rule, we have several candidate models. So, for instance, available at GitHub, or even, well, suggested by ourselves. Several different models of different architecture, for instance. Models which would be trained on different data, pre-trained, for example. Yeah, you remember we follow this 3R framework. Yeah, recycle, reduce, and reuse. So we have several models, and very often our goal in research and development is to find the best performing one. Best performing is with our data. So then how we solve this problem? So, okay, we get retrained models, or candidate models. So we train them with our data, for instance, fine-tune or train from scratch. And we do some benchmarking experiments. Benchmarking. You already did it, Many graduation projects involve some benchmarking, so student graduation projects, right? Your teachers told you, okay, you need to compare several models, and you need to find which one works best, yes? And what is benchmarking? It's shown here, So, for instance, how typically, what benchmarking means in the context of an AI model research. So benchmarking, that means that, well, okay, we have some data, our data, for which we want to find the best model. So best performing model which would produce best values of some metrics, accuracy, precision, so F1, micro, something like that. And then we do just some sort of brute force testing. Each and every model what we have, we train it with our data, we run it on the so-called unseen data set. Unseen, that means that new data, yes, so which was not used in the training process. And then we compute the metrics. So, and we compare the metrics and we find out, yes, so what model was the best. And well, the more models we have, the more harmful it is. So in terms of the environmental impact, carbon footprint, and common sense even. Yes, so because here there are no limitations. On the one hand, how many models we would test, no limitations other than, let's say, our time, yeah, so, and resources available. On the other hand, still there is no theory, no textbook, yeah, so which would tell us, yeah, how to select based on some theoretical considerations what AI model would be best, yeah, so for our data. So benchmarking, yes, so with all its inefficiency, remains at the moment the only method, yes, so which is used pretty much by everyone who develops artificial intelligence models, and a very harmful, yeah, and inefficient, yes, so method for the assessment of AI models. So, yeah, it was clear to us, yes, so from the very beginning, but then, okay, what could we do here? And a solution came from a metaphor. What is benchmarking? What is similar to AI benchmarking, model benchmarking? It's similar to hiring people by an organization. In our research, we would like to hire the best performing model, right? So we want a model which would perform best. So organizations, companies, governmental institutions, so they also want to hire young people and not so young people who would perform best, who would do certain things, certain jobs, so well, most efficiently, so with minimum retraining or training required. So that means that personal selection is very similar conceptually to the model benchmarking process. So organizations, well, they have human resources department, so which search for and find new employees. So, and we, AI researchers, we have what? Well, we have GitHub and the World Wide Web resources, right? Yes, so to find models, candidate models, yes, so, and then we have benchmarking, yes, so with our data, so to decide on the best performing model. So then, personal hiring was a research topic in social sciences, in management sciences, yes, so more than 70 years ago. It's in the 1950s. This is when some kind of like, well, most fundamental social research was done in this field. Lots of methods and tests and methodologies, yes, so were developed and proposed. And ever since, approximately beginning from 1960s, so all serious organizations worldwide, so, well, they follow the theoretical findings in hiring their personnel. So then, what is a typical structure of personal hiring by an organization? What are the typical stages, steps? Okay, so as always, it begins with needs identification. That means that, okay, should we hire somebody or not? And if we should, for what? What kind of jobs? So next, scouting, yes, so means that advertising, yes, so like, well, attracting the applicants. So next step, document screening or preliminary screening, just based on the applications, what are received, yes, so for the jobs. human resources do that. So next, initial selection. What is this? This is interviews and basic skill assessments. Basic skills. Not really like what the employees would really be doing, yes, or in the organization, but very basic skills, such as, for instance, some arithmetic skills, such as logical thinking, something, yeah. So these skills are usually tested, yes, so on proxy assessment tasks, proxy skill assessment tasks. So next, based on the results of these assessments, so, well, the successful applicants are selected and hired and, well, given jobs at the organization. So this is a structure for human personal hiring. Yes, so then here we have benchmarking. So, well, just let's ignore the first two stages because the World Wide Web provides us with the resources and naturally we would have some data, yes, so, well, for our research, but we have kind of screening. Yes, so screening means that when we look for models, and from all the models available somewhere at GitHub, yes, or just at our disposal in our research, yes, so we select the possible candidate models for our data. And then in conventional benchmarking, we try each and every model, right? So we kind of, in benchmarking, we don't have these two steps. So we don't have any interviews with the models. We don't have proxy assessments, proxy basic skill assessment tasks. We don't have it. So right away, we just deploy the models, all candidate models with our data and see which one would perform best. So that means that, okay, yes, so we started to think, could we find some simple means that not requiring a lot of computation. So simple tests, simple metrics, which would allow us quickly pre-screen, preliminary assess, yes, so, and filter out candidate models which would definitely not perform well with our data before benchmarking them, deploying them, yes, so in our experiments. And here, that's, well, how we came to the idea, the so-called language model data fit benchmarking. We introduced two additional steps into the benchmarking. Yes, so, well, one, preliminary selection. So that's where all candidate models, they are subjected to fitness assessment and some metrics are quickly computed, yes, so for each of the model. And based on the metrics, so in the next step, all candidate models so are divided into two groups, more fit and less fit. So less fit models, so they are then excluded from the consideration. So, and only more fit models are then deployed in the benchmarking experiments. And, well, the result of the benchmarking is the selection of the best performing model, of course. So, but then how could we? What does it mean, model fitness, AI model fitness? So, well, this is where some difficulties begin. When I say an AI model, I mean, of course, it's a neural network model. So, because in these days, by far, this is the most dominant models in the field of artificial intelligence. So then, each neural network model, would it be For instance, yes, so deep CNN or deep RNN, yes, so, or any other type of neural network model. So it has parameters, right? So what are AI model parameters? How do you understand it? What is this? AI model parameters, what is this? Tell me. These are what? Weights, yeah? Weights. Of course, there are some other parameters, but 99.9% of the parameters of an AI model, these are weights. So what the model learns, this is where the machine learning comes, yeah? So what? Through training, yes, so well. It learns, yes, so well, when it's subjected to the training data. So how many parameters an average AI model, modern AI model, so has? Well, guys, you trained already AI models. Tell me how many parameters, roughly? Hundreds of millions and billions even, right? At least 100 of millions. Yeah, that's, yeah. Okay. Then, to talk about fitness of machine learning models, I need to introduce the concept of the embedding space. Have you heard about that? Yeah? Then what is this, an embedding space? It's a very complicated concept, actually. So it's very difficult to define it using just common sense words, but I will still try. So you could think about an embedding space of a model as a reduced parameter space. So there are hundreds of millions of parameters, right? So, but then some of the parameters are more important than others, especially when we talk about a particular task for what the model was trained. So then, if we think about all parameters as dimensions, because, yeah, well, parameters could take some values, and since parameters, these are variables, that means these are dimensions in that multi-dimensional space with hundreds of millions or billions dimensions. So then, well, for every particular task, we would do some sort of dimensionality reduction. We just identify the most important dimensions so that we only leave those dimensions, so which would influence the performance of the model. So then this reduced dimensionality parameter space could be called embedding space. For instance, here in this example, this is a visualization of the embedding space of a speech recognition model. So this model was trained to recognize only digits in English. It ignores any other sounds, but only digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So the 10 digits. So then each dot in this visualization of the embedding space of that model corresponds to a location in the embedding space. So location of the output corresponding to a specific input which was supplied to the model. The input here, this is speech. Output, this is the name of the digit itself. And we can see that in the embedding space, just as the model was actually deployed, as it worked, so, well, similar inputs kind of like, well, they're placed together. Yes? That's the whole idea of the embedding space, that inputs which resemble each other, they are located closer in the model's embedding space. So, yeah, That's how classifier systems work. So, well, there is embedding space, similar things are placed or represented, yes, so closer, represented in close proximity in this space, so by the classifier system. Okay, we now remember what is this embedding space. Embedding space, this is what? Reduced dimensionality feature space or parameter space. Next, go to the model fitness. Look, for instance, this is kind of like very much simplified, so 2D representation of the embedding space of a model. So then we have two locations here in this embedding space corresponding to two different inputs to the model. For instance, this would be two images. So then one of the standard tasks in artificial intelligence is so-called similarity assessment. So how similar this image is to that image? How similar this document to that document? So how would we solve this problem using the embedding space of a model? Yeah, we would just, for example, compute the locations, yes, so of the input vectors in the space, and then assess the angle, yes, so of the vector representation in the embedding space. We would compute the so-called cosine similarity. More similar inputs would what? Would be located closer to one another, right? So, and that means the angle would be smaller and smaller, yeah. Then cosine would be greater and greater, right? Yes, so that's why it's called cosine similarity. Cosine similarity can be computed pretty much with any AI model. So would it be, well, text classification, image classification, speech classification, sound classification, whatever, yes, so whatever AI model we use. So we can compute cosine similarity of inputs. Then, okay, the last preliminary thing was next. How could we then understand if the model what we have is good for our data or not so good for our data? So, or reformulating it a little bit, how could we understand if we have several models, so which of the models would definitely be not good to our data? So, to answer this question, so we need to look a little bit into some fundamentals of machine learning, fundamentals, mathematical, yes, so foundations, so of machine learning. And well, it was found that for any embedding space, for any AI model, for a random sample of data, the distribution of the cosine similarity metric is Gaussian, normal. So normal means what? Bell-shaped, right? Yes, so this is normal distribution, right? Yes. So then, if we have two different models, we take random sample from our data. We expect that, well, both models would produce Gaussian distribution, yes, of the cosine similarity if we compute the cosine similarity for our random sample of data. However, look, for instance, here we have two models. Cosine similarity is a metric which is bound on the unit interval. For theoretically speaking, cosine similarity changes from -1 to 1. So, but for most of the AI models, yes, so it changes from 0 to 1. So 0, this is for completely dissimilar, yes, so well, inputs, and 1 is for identical inputs. So then we have two models, green here, for example, and blue one. The distributions, yes, so of cosine similarity computed for the same random sample of data. Green model here is better. Why? Because the blue one, the average cosine similarity, yes, so is higher, closer to 1. That means that the blue model here, yes, so would have difficulties so to differentiate the data, to find differences. Most of the data for the blue model would be similar, the same. It would be a worse classifier so than the green model. At the same time, however, would be a situation like that as well. We expect that the distribution is Gaussian, that means symmetric. So, however, well, in reality, since we never know, yes, so what kind of data we have, so we take a random sample. It's not necessarily purely Gaussian, yes, so it could not necessarily be symmetric. So, for instance, due to the fact that the distribution itself so is truncated. Truncated means that it's bound on the unit interval. It's just from 0 to 1. Yeah. So then, in reality, there would be some skewness in the distribution of the cosine similarity. Skewness means that asymmetry, just as in this case. Look, the green distribution here, corresponding to one model, is symmetric, and the blue distribution has a skew. We say negative skew, yes, so left skew here in this case. So that means negative skew is asymmetric with kind of like, well, heavier, yes, so tail, yes, so to the left. And the blue model would be worse than the green one in this case. Why? Because it kind of overfitting here. It would differentiate, yes, so too many documents. So it would have poor generalization ability. Again, a poor classifier here, a worse classifier than the green model. So then what we have? We have one statistic, that's the mean, the average value, yes, of the cosine similarity, and another statistic which is called skewness of the cosine similarity distribution, so which tell us which model is no good, would be no good for the data, yes, so what we have. Would be no good in terms of the differentiation and in terms of the generalization. Okay, so then, just one more thing to remember. These two statistics, the average value, the mean, and skewness, they are not correlated. That means that, well, the mean would go up, skewness would go down, so, or whatever, yes, so mean would not change, but skewness would increase, for example, or decrease. They are not correlated at all. So that means that we cannot use these statistics, yes, so kind of like, well, in one replacing another way, yeah, so we always need to use them together. So, and we cannot use them separately to rank our models, just based on judgments or assessment of just one statistic, say that, okay, this model is better than that model. So instead, what we can try to do, we can try to compute these statistics for all candidate models, and after that, do some sort of unsupervised cluster analysis. So to break all the models based on these two statistics into less fit models with poor generalization or classification abilities, and more fit models. So based on the similarity assessment in the embedding space of each model. So this is about k-means clustering. Guys, do you know how k-means clustering works? Some of you know, some of you not, right? I just remind you. We have two statistics which are computed from cosine similarity values for a random sample of data. So for each of the candidate models. So that means that each dot here in this two-dimensional space. Each dot corresponds to a model, machine learning model, to a specific embedding space. So then K-means begins with what? Two random locations for centroids, right? Centers of the clusters. Okay, two random locations. Next step, K-means clustering. What? Distances are measured, Euclidean distances, for instance. Yes, so, well, Euclidean distances are measured from the centroids to each of the points, so what we intend to cluster. So, for example, for this point, well, it's closer to the red centroid. So then, well, this point is classified as belonging to the red cluster. So then the same procedure is repeated for each of the points, where each point corresponds to a model. And this is what we have after all of the points are assigned to the centroids. Okay, now we have already two clusters, but it's not yet done. No, this kind of like, no, inaccurate clustering yet, because the centroids were assigned what? Randomly. Next step, centroid points, these points, yes, so which were assigned randomly, recomputed. Recomputed as the actual centers of the clusters. We have two clusters here, blue and red. So they are recomputed, and now this is the new centroid, and this is new centroid for the other cluster. So then again, the same procedure is repeated. Distances are measured, yes, so cluster assignments are made, and finally, well, we have all the models. Each data point here corresponds to a model, machine learning model, right? Yes, so, well, all the models are broken into two classes. So, less fit and more fit. Okay, it looks like we can now go already and try this method in practice. However, not yet. You remember that we compute similarity, cosine similarity, based on a random sample, right? We take a random sample of data, yes, from our data, and then we compute cosine similarity. Unfortunately, cosine similarity is a statistic which is, for some data, not very easy to compute. It's very fast, but not very easy. For instance, when we compute cosine similarity of two documents, and documents have different sizes, so we have to kind of like, well, normalize document representation to a vector representation. So there would be, we can only compare vectors, right? And the vectors must have the same length. So if we talk about documents and language processing, yes, so well, most of the language models which are widely used in these days, they have the dimensionality of the embedding space equal to 768 or a little bit higher, yes, so around 1,000 dimensions. So then we have these vectors, yes, so, well, also kind of like normalized, yes, so, well, it's even for long documents and for short documents, we have the same length vectors in this space. So, and then, well, what we get in this case that depending on the data size, for example, on the document size, so, well, the would be errors in similarity assessment. So if the errors are random, it's okay. There would be no bias, there would be just noise, and still our method would work. So, but if, for example, in the sample we have way too many, let's say, short documents, so then our assessment would be biased, yeah, so, and our method may not work. So to minimize the influence of the some different data size, yes, so on the cosine similarity assessment, yes, so instead of just random sampling, yes, so from our data for computing cosine similarity, we do stratified sampling. What is this stratified? Stratified means that, well, First, we compute the strata. We analyze our data sample, and for instance, in terms of the document length. And then, well, we break all the data into strata where the documents of the same or similar size are stored together. So then when we use random sampling, we make sure that each of the strata, represented equally, so in the random sample, what we use for computing cosine similarity. So then by doing stratified sampling, we kind of like minimize the bias, so in cosine similarity assessment, which would be due to the sample size and the sample composition. Now we are almost ready to apply this method then in practice. So, well, we got, so far, these were all theoretical ideas about how we would use it. But then we decided to test it with real models, with real data. We limited our experiments to language models. So then we used quite a lot of different data. Different means that, well, these are language models, means our data was texts. Different data from different domains. So used benchmark data, so from shared resources, so which were used in quite a lot of research previously, so in benchmarking experiments by different researchers. So we also used these 7 models, which were pre-trained, with different data. So we use these 7 models. Why? Because they are, well, among the most popular models, first of all, in natural language processing. So they have the same number of parameters, so that means it's easy to compare. So the same number of dimensions of the embedding space, and many other similarities. They are all, of course, for English language model, for the English language. This is the data what we used. So the data, well, again, as I said, very different. And benchmark collections, well, for binary classification, but also for multi-class classification from different domains and, well, kind of different composition of the data. I said that we are almost ready to run our method already. One thing what I still didn't tell you, well, I said we need a random sample from the data to compute cosine similarity, right, distribution. But how many data should be? How many data points should be in this random data sample? Well, we of course would say, okay, let's get 100 points. Let's get 1,000 points, but it wouldn't have any meaning, right? To understand how many data points we should have, so we conducted some preliminary experiments where we monitored the two statistics, the skewness and mean of the cosine similarity, computed, so based on the data, and then we changed the size of the random sample. And we observed that, okay, beginning from approximately 200 documents in the random sample, so the statistics do not change too much. Still, there are some changes, of course, so even after 200, but these changes already not as much dramatic, as before 200. So we decided to use 200 documents random sample to compute cosine similarity distribution. 200 documents looks like not many. However, so if you remember combinatorics, if we compare each and every document with every other document from the 200 samples, so we need to perform almost 20,000 comparisons. That means that almost 20,000, so cosine similarity statistics need to be computed. Fortunately, for any pre-trained model, it's kind of a very easy task. It's done like in less than 1 second, yeah. So for any machine learning model, yeah, so to compute these 20,000, yeah, so statistics. We did these experiments, and here's just visualization, yeah, so an example of what we did. We worked with 7 different models, and we worked with 8 different data sets, and our goal was like, okay, to see how our method of breaking the models into less fit and more fit, yes, so works in terms of the benchmark. Here's just an illustration for 3 models. For example, well, these are the cosine similarity distributions computed for 3 models. You see that here, for instance, the green model obviously is no good. Why? Because almost all documents from the random sample are similar, yes, so, well, too similar, yes, so based on this model. So if we do clustering here, K means clustering, yes, so, well, again, it easily breaks. So K means clustering with K equal to 2 into 2 classes and says that, okay, exclude this model, less fit model, the green one here, from further consideration, from further benchmarking, because, well, it has a poor generalization ability, poor differentiation ability. The 2 other models, blue and red, for instance, here, yeah, they need to be tested, yes, so to understand the best performing one. And we did it with each and every model and with each and every data set, and here is just a summary of what we found. Yes, so that's, well, on average, by applying our method and cutting the less fit models from benchmarking, so we would save approximately 37% of the resources. That means that the emission cut, yeah, carbon footprint cut, on average, yes, so, well, would be cut by 37%. By applying our method. It's quite a lot. It's more than 1/3. So, less fit models were thrown away from benchmark based on just cosine similarity statistic compute. So, well, limitations of the approach. First of all, this approach cannot be used to replace benchmarking completely. Just based on cosine similarity statistic, we cannot say which model would perform the best. We can only say which models would perform no good, yes, so with few data. We cannot rank the models based on our method, based on these statistics, no. For ranking, you would still need to do the traditional benchmarking, so with the more fit models. So, and you would need to use the traditional metrics like F1 or accuracy scores. So, we also didn't test this approach with models other than language models. Language BERT models, transformer models. However, we are pretty much sure that since, well, all classifier models, they have the embedding space where the similarity, cosine similarity statistics can be computed, we are pretty much sure, yes, sir, that, well, it would also work. We are planning, of course, to conduct experiments with image classifiers, with speech classifiers, for instance, but, well, even if this is a limitation of this particular study, so here we do not expect any particular, let's say, bad surprises, yes, so from this method. So finally, to conclude, when you conduct AI research, when you experiment with machine learning models, be responsible. You don't need to run around and just shout, yeah, green AI or whatever. So, but please just remember about 3R framework, yeah, reduce, recycle, reuse. So try to recycle and reuse the models whenever possible. Next message. Yeah, now you know, yeah, at least one method which works in practice and which helps minimize the environmental impact when you benchmark models. The details of this method you can find using this URL, and this is open access. Yes, so it's a journal publication, so published in January this year, so it means very fresh. So furthermore, all the resources, all the source code, Python source code, yes, so what can be used, what should be used to implement language model data fit in practice, yes, so well, you can get it, yes, so from GitHub, yes, so using this URL. And one interesting note in the very end to make you feel a little bit better, yeah, so this method was developed. The lead researcher, yes, so of this project is an Indonesian doctoral student. Yes. So, an Indonesian, yes. An Indonesian who graduated from, no, not Brawijaya, from Telkom. His undergraduate was at Telkom, but quite many years ago. Yes, so, and well, I'm talking to you guys in Indonesia about not all results, but the main results, yes, so obtained by an Indonesian researcher. Yeah, an encouraging fact. And I hope you would use these results, yes, so, well, in your research. And maybe, well, somehow even improve this method, extend it, yes, so, and so on and so forth. That's it for now. And I'm ready to answer your difficult questions, please. Not too much time left for the questions, but still.
Ya, silakan mungkin ada satu atau dua pertanyaan. Oh ya.
And one more is then later. Yeah, so, okay. Yeah, please.
Hello, sir. Konnichiwa.
Hello. Yeah. So,
Bahasa. Actually, sir, what is the main difference between red AI and green AI? Yeah.
Red AI, the focus is on the performance. That's it. Green AI, performance plus minimizing the environmental impact. So just one more optimization criterion is added in green AI. Green AI, of course, also it's about performance, but at the same time also, well, finding so the least harmful methods. That's the difference. Okay? Okay. I think.
All right. First of all, thank you, Professor, for the lecture. It was very insightful and inspiring. I am Siti Zakia. I'm a master's student here in Faculty of Computer Science, Universitas Brawijaya, and I have a question I wish to ask you. You have emphasis before the importance of efficient AI architecture to make sure we reduce carbon emissions and prevent all kind of environmental problems, hence why the sustainable and green AI. So aside from that, I have noticed some other cases where efficient AI architecture is very important right now. I myself is dwelling in virtual reality researches, and recently the emerging trend research for my field is how we can make intelligent digital avatars in virtual environments that can help us human beings and assist us with tasks. But usually that kind of avatars use large language models and AI system as its brain. And this is where the researchers in my field face problems. It is so hard to find AI systems that is efficient, have high accuracy, but doesn't force us to use advanced hardware only. Usually, if we want high accuracy, it will force us to use advanced hardware, but that means our works won't be accessible to the major population. So my question is, with how things are going right now, both with green AI and sustainability, and also how we have more increasing demands on to make AI system integration to other systems easier, do you think sooner or later we will see a major paradigm shifts where we put more emphasis on architecture efficiency in AI rather than just sheer accuracy only? And may I know what do you think that will affect the industry adaptation and how it will affect us researchers in the future here in academic circles? Thank you.
Thank you. Thank you for quite an interesting note in the beginning. Yes. Well, as I already mentioned in the beginning of this lecture, yes, there is no free cheese, right? Yes, sir. That means that it's easy to say, let's be green. Yeah? Once we try to, for instance, with avatars or other things, yes, so very often we just find it out that, okay, yes, sir, we actually, well, not really making it any greener. Yeah. So, but then your question is, should we expect a paradigm shift or not, right? That's a very difficult question. Yes, so it depends on you know who, on the contributors to the GitHub, to the community. So it depends on those who supply in these days, yes, or the models which are then reused by the great many researchers. Who are these people? Of course, all of us, but mainly, so the models what we, well, let's say, modify, reuse, yeah, recycle, yes, so the original models are created by very few select research centers, such as Google, such as Microsoft, as we know, right? So it depends on them, I can say. So what we now see, unfortunately, the trend is a bit opposite. So, for instance, the OpenAI initiative, right? They do not even talk, yes, or about greenness or something like that. They don't care, at least publicly, about that. So, chatbot GPT, yeah? You guys, useful product, right? Yes? So, large language models, useful, yes, of course. But, well, again, we only start thinking about little bit, even indirectly, about the greenness of large language models when we find out that, okay, our computing environment is not sufficient to run, yeah, for instance, chatbots, yes, or something. Only then we start looking like for some, well, let's say, open source and simple alternatives, yes, or start thinking, yeah, okay, what else could I do, right? So that means that your question is a good question, but again, it depends, of course, on us, but also depends on the major players. Major players means that these leading research communities, unless they start, I hope, yes, so yeah, they will start implementing. They will make, you know, yes, so it's kind of a rule sooner or later. It's the same, by the way, how it became in manufacturing. I began my lecture like with this 3R framework, which comes from green manufacturing. 25, 30 years ago, it was also the same in that field. Like, you know, we don't really care that much about the environment. But now, yeah, I would say that manufacturing is quite responsible. Even like garbage utilization, yes, so there are lots of right steps in that direction, yes. So let's hope. My answer is let's hope. But not soon, no, not soon, definitely not. I don't expect it very soon, unfortunately.
Okay, thank you. I think that's enough for today, Professor. That's okay?
Fine with me, yes. Yeah, so then, thank you very much, guys. And if you feel, of course, it's difficult right away to understand. It was quite dense. So nobody remembers statistics, all this skewness, right? Yes, so what is skewness, by the way? Stratified sampling. These are standard methods. But, well, my advice to you, please read this paper. So if you would like to use, and I strongly recommend you, please use this method in your benchmarking. So get the source code. If something is unclear, send me an email. My email address is, you can find it in the publication. That's all. Thank you.
Okay, thank you very much, Professor.
Yes, so guys, please don't run.